Hello. In this session, I'd like to discuss just a few more details to do with the ANOVA table and some useful relationships we might learn about and one or two extra things that we can calculate from the ANOVA table. And once we've done that, we'll move on to talking about predicting responses and how we can do that using, well, two different types of interval estimation techniques. Okay. When we talked about the simple linear regression model, we spent some time discussing about how to estimate sigma squared. And we said we used what we might call the model-based estimate, and we call that, of course, S squared. So we had an explicit formula in the simple linear regression case, and what I'd like to do now is derive the same formula for multiple regression models. The formula is this. It's the sum from I equals 1 to n of yi minus y hat I, remember these are the fitted values, divided by n minus p. This is the number of observations minus the number of betas you're estimating, and you include the intercept in that number. If you look at this formula and look at the formula that we had for the sums of squares for error, what in fact this is the sums of squares for error divided by n minus p. In other words, it is the mean square for error, the entry in our ANOVA table that we call the mean square for error. So the estimate of sigma squared that we call S squared, which is based on the fitted model, turns out is exactly the mean square for error. In the simple linear regression case, by the way, we would have the sums of squares for error, this formula here, divided by n minus 2, because in that case there's always two parameters in the model, and so this is a generic formula that works for all regression models. There's nothing special or unique about the simple linear regression case in this regard. We actually can use this to take, for example, the OR output given by the summary function and recover or reconstruct the entire ANOVA table if we want. Of course, we can always use the ANOVA tab function that we used previously, but can we just see how that works? So what I'll do is we'll go to OR, and I'm going to use some code here to read in the dose response data. So we set our working directory and so on, we read in the data, and I've also read in the ANOVA tab function, but I'm not going to use it just yet. And then I use the summary function, and of course I get the output we've looked at before, and we've interpreted this. Let me just copy this in again and show you how you might recover the entire ANOVA table from this. So here's the output, and of course we have the summary values towards the bottom half of this output, and I'm going to in particular pick out some parts here. The entire last line is relevant to me. And I want as well this here, what's called the residual standard error. Okay, why do I want these? Well, let me just annotate these. The residual standard error presented here is S, or if you like, the square root of S squared. So that's 182.7. If I square that, I get S squared. Okay, that's the first thing. It's called a residual standard error, or S. It's a square root of S squared. This is the F ratio statistic, and of course we have the p-value, and as well as that I'm given the correct degrees of freedom. And I think from this I can recover the entire ANOVA table, as we said. Right, let's see how that goes. So remember how it's constructed. We have a source column, degrees of freedom, sums of squares, mean square, F, and particularly when you're using the software as we are here, the p-value. Well, the p-value is here. It's 0.0006 as we've seen before. The F ratio is here. It's 21.45. Now, I think I can fill in the value for a couple of other entries in the tables, and from that get everything else that I need. So we have one of the sources, of course, is the model. We have the error, and in fact I'll also get the total. How do I fill in the values? Well, if this is S, or the square root of S squared, we said that S squared is also the mean square for error. So it's equal, this value here is equal to the square root of the mean square for error. So one way of getting this is to square this value and fill that in for the mean square for error. So let's do that now. We need to square 182.7. Big number. So we have 33,379. I won't worry about decimal places too much. 33,379. Check that. Yeah. That is the mean square for error. We also know the 2 degrees of freedom. They are 2 and 8 respectively. You can say there's 10 for total. How can I recover the rest? Well, how do I get the model mean square? The model mean square divided by the error mean square gives me this F ratio 21.45. So I have a situation like this. X divided by the mean square for error is equal to F. I have an equation. How do you solve an equation like this? Where you have a fraction on one side and a number on the other? Well, you cross multiply. Therefore, the unknown X is equal to the mean square for error times the F ratio statistic. In other words, I can get the mean square for a model by multiplying 21.45 by this 33,379. Let's have a go. Just multiply that last answer by 21.45. 715,986, I'll call it. 715,986. The sums of squares are divided by the degree of freedom to give us the mean square. So if I want to get the sums of squares back, I multiply the mean squares by the degree of freedom. So I'll multiply this answer by 2. 1,431,971. So 1,431,970. Well, 972. Just round to the nearest whole number because it's quite big. And in the same way, the sums of squares for error divided by 8 give me the mean square for error. So I can recover the sums of squares by multiplying the mean squares by the degrees of freedom. So in that case, it's 33,379 times 8, 267,032. 267,032. So this is the entire ANOVA table, if we've got that right. And we can do this for the other models as well, the bread wrapper data, for example. We can do exactly the same thing if you want for the LDL data. So all this is possible to do for any model. We'll go and check our answer, I think, by going back to OR, and I'll use my ANOVA tab function. And let's copy and paste this in and just compare the two answers. Let's have a look. Yeah. So there's a little bit of rounding error going on here, but other than that, I think we're pretty accurate. 21.45, yeah, 21.4, 33,379, a little bit out, 33,368. It's just rounding error due to the squaring things and multiplying them, but only carrying 2 or 3 decimal places. But you can see that given a bit of rounding error, which isn't too bad given the numbers we're looking at here, they're only low percentage rounding errors, we're essentially getting the same answer. And from this, we can calculate certain other things. So this is basically the exercise you go through to recover the ANOVA table by hand, if you like, from the default or output. Or, of course, you can use this ANOVA tab function to get all those decimal places carried, so you get slightly more accurate answers. One statistic you can calculate is a famous statistic that we'll talk about a little bit later on called R squared. So R squared is equal to the sums of squares for model divided by the sums of squares total. Incidentally, this sums of squares for total is the standard one, so I haven't qualified its name. Technically, it's a sums of squares total corrected. There is an uncorrected version, but that uncorrected version is only rarely used, so I didn't bother qualifying the name in this case, and that's fairly standard. That's equal to, in this case, it's the 1,431,214 divided by 1,698,155. So I literally divide the sums of squares model by the sums of squares total to calculate this statistic called R squared. Let's just do that. There, 1,431,214 divided by 1,698,155. 0.842. 0.842. So that's the R squared statistic in this case. What is it? R squared is the percentage of total variability in the response which is explained by the regression relationship. So it has this very intuitive interpretation, and therefore it's very appealing to many people doing data analysis, that they like to look at their R squared value and work out, well, I have a response and there's differences in the response between my observations. How much of that difference am I explaining by modeling what's going on in the response with reference to the predictor variables? So how much can they explain with my model? And the answer here is, well, it's 84%. We'll talk about how people have tried to use that in model building later on. It is a useful statistic, and it has that nice intuitive explanation and definition. However, be careful. What is a good or high value of R squared is highly dependent on the the data you're analyzing. For example, in a very controlled chemical, maybe experiment, lab-based, it may be quite common to see quite high values of R squared. There is some background variability that cannot be explained, but you want to explain a lot with your predictors, which may be sort of reagents going into the chemical reaction or something like that. But in other areas where you have less experimental control, for example, the social sciences are a particularly good example, you rarely get R squared values that are very high. They might be 0.25, 0.26. They could still be coming from models that represent incredibly useful things in making decisions or spotting trends within the population you're studying, but nevertheless they will look small compared to other data examples. So just because an R squared value looks fairly low compared to another one doesn't mean that the model is poor or not going to do its good job. And just because an R squared value is particularly high doesn't mean necessarily you've got a great model either. So be a little bit cautious in its interpretation. One more thing. There's a particular interpretation of R squared in the simple linear regression case. So in the simple linear regression case, R squared is equal to rho squared, where rho is the Pearson, in other words, the standard one, correlation coefficient. Okay, so in this particular case, in the simple linear regression case, R squared actually is equal to rho squared. It's the square of the Pearson correlation coefficient. And if you remember, the Pearson correlation coefficient is a measure of how strong a linear relationship is between the predictor and the response. A perfect one would be either 1 or -1, so it's assigned. If the relationship is positive, it's positive. If the relationship is negative, it's negative. But we know that as it approaches either 1 or -1, the linear relationship between the two variables, the predictor and the response, is approaching a perfectly straight line. If it's close to 0, there's very little relationship between the two variables. That's a straight line relationship, and we interpret the intermediate values accordingly. So it's a scaled measure of the strength of the linear relationship. So in this case, we could just simply take the square root of R squared and say, well, we don't know the sign, other than looking at the sign on the beta 1 estimate, but that will give us the unsigned, in other words, absolute value of the Pearson correlation coefficient. What it means in the regression framework is a little bit more complicated, but I think that the handiest way of remembering it is R squared itself, rather than trying to reduce it to a Pearson correlation coefficient or some analogy of it. R squared is the percentage of the variability in the data in the response, which is explained by a regression model on the predictors. Well, okay. Let's move on to the second part. Predicting responses. How do you predict a response given a set of predictors. So I'm assuming that maybe you're dealing with a multiple regression model. Well, we initially start off by use the fitted values. In other words, predicted response we'll call y hat I, also known as the fitted value. We've used these before, of course. And y hat I is equal to beta hat naught plus beta hat 1 xi1 plus beta hat 2 xi2 plus, and I'll just use the ellipses there, the 3 or 4 full stops to indicate you keep going that way. So in a multiple regression model, what you do is you take the values of your predictor variables and you plug them into your least squares formula, and you get what we call the fitted value. And in fact, that fitted value is the best predicted value for your response. Let's have an example. Predict the activity level for a dose of 40. Obviously, this is the dose response data. Okay, so what I'm imagining here is that having fitted the model and you're happy with the model in its current form, the next step is to say, well, I want to predict the response in the subject, which are the rats in this case, if we give them a dose of 40 of this steroid. What would we expect their response to be? Well, let's go back to OR and get the parameter estimates. Here they are here. So let me just take them down. The intercept is 430. Beta hat 1 is 69.5. Again, I'm going to round a little bit here, and we'll get the exact answer from the software very soon. And beta hat 2 is minus 0.817. So we have a linear equation then, and I go, okay, well, we'll go y hat I, and I'll actually specify that xi is equal to 40. So in this particular case is equal to, well, it's beta hat naught, so it's 430 plus 69.5 times 40 minus 0.817, and that's multiplied by 40 squared. So 430 plus 69.5 minus 0.817 times 40 squared. Let me just repeat that calculation for a second. Yep, just made a mistake there. I forgot to multiply the 69.5 by 40, didn't I? Let's see how we get on now. Yeah, 1902.8. Let's go back to OR and see how that corresponds with the sort of picture we drew of the fit to the dose response data. So what I'll do is I'll get a plot of this. So we have a plot of Dior activity. Actually, it's the dose first, of course, isn't it? Dose against Dior activity. Put in my usual solid circles as plotting characters. I think that should give us a reasonable plot initially. Yeah, I'll just make them a little bit bigger. There we go. So we have a reasonable plot down here of the dose response data again. And then I'll add my curve. So it's a curve, it's 430 plus 69. What do we use? 69.5 times x minus 0.817 times x squared. I'll make it a reasonably thick line. The color will be the usual red that we use. And of course, importantly, we add it to the current plot window. I think that should do the job for us. Oh yes, from and to. From equals 10 to equals 80. I have to tell it the range across which I want to do the curve sketch. There we go. Right, so we put it in here. Now, how does that value of basically 1900 relate to this? Well, what's happened here is we have gone to x equal to 40 and we've projected up until we've hit the actual fitted function, and then we have gone across from there and we've read off over here. Do that a little bit better. There we go. It would be there. So it goes up until we hit the function, and then we go across, and basically that value there where it hits the vertical axis, so this one here is basically 1000 and what was it, 1902. That's what's happened. So the fitted value, which is our best prediction of the response given a value for a predictor, is the value on the fitted function above the value on the x-axis. In the multidimensional case, this is, for example, like the bread wrapper data. What you would do is give values for both x1, the sealing temperature, x2, the percentage polyethylene, and you would project up from the floor of the 3D space until you hit the fitted plane, for example, and the height that at which it hits the plane would be the predicted response in that case. And of course, if you were using the curved surface model in 3D, you would project up until you hit the curved surface model. So it's a projection from the values of x onto the fitted function that you're using in your particular model, and the height where it hits that fitted function is essentially the predicted value, also called the fitted value. Well, that makes sense, but what if I want a confidence interval for that? I mean, that's a very exact calculation we did up here, 1902.8, but could it be within a wide range in reality around that? Surely there should be some error in the estimation of this value. And so perhaps what we'd like to do is come along and use error bars. So we may want to say, well, look, that's our estimate, all right, but I want to put in error bars around this, which represents a confidence interval. In that estimation. How do I go about doing that? Okay, so how do I get a confidence interval for my predicted value or fitted value? So I want a confidence interval for this. I'll call it fitted values. okay, for this fitted value. How do we get that confidence interval? Well, it's going to be y hat I plus or minus a t quantile, 1 minus alpha over 2 degrees of freedom equal to n minus p. So an appropriate value from the t distribution, because remember it'll be a t-based confidence interval, times what's called the standard error of the fitted value. And this can be written as as the square root of the variance of y hat I. Now the question is, how do I get the variance of y hat I? So the variance of y hat I, just to give you an indication of how we do it mathematically, is the variance, and I'll just use our example, of beta hat naught plus beta hat 1 times 40 plus beta hat 2 times 40 squared. Okay, and when you work through the mathematics on that, it becomes a little bit complex. We'll have the variance of beta hat naught. Now remember where we can get them. We can get the variance of beta hat naught from the variance covariance matrix we discussed before. Plus, it would be the variance of beta hat 1 times 40 squared. No, you might think I made an error there. It should be 40, not 40 squared. But in fact, whenever you take the variance of a random variable times a number, you need to square the number. Plus the variance of beta hat 2 times 40 to the power of 4, because you have to square it, of course. We're not done yet. Plus twice the covariance of beta hat naught with beta hat 1 times 40, plus twice the covariance of beta hat naught with beta hat 2 times 40 squared, plus twice the covariance of beta hat 1 times beta hat 2 multiplied by 40 and 40 squared. Okay, so it's a mess. Luckily, we don't have to do this. Okay, luckily we don't have to do this in practice. We simply rely on the software and some results from linear algebra that make the calculation of this reasonably efficient. So, nice. So let's go and, so what we need to do is calculate all this. Yeah. And then we'd be using this quantile here from the t distribution. By the way, that's exactly the same as the critical value we use in the individual parameter t-tests, assuming you're using the usual 5% level for alpha. So that's nothing new there. We'd calculate this variance. We would take its square root to get the standard error, and we plug it into this formula. And when we add and subtract it from y hat I, of course, we'll get an interval around our 1902.8, and that would represent a 95% confidence interval for that fitted value or predicted value. Let's go to the software and get it to do the hard work for us. And in fact, I have it done down here. Yeah. So what we do is we can use a nice function called the predict function to do all this work for us. And that's what I'm doing in this line here in line 18. So I have predict, and predict from what fitted model? Well, it's fit underscore dr, the dose response model. And then you say, well, what values do you want to use for x in this prediction? So this is called the new data function or new data argument. New data is equal to, and what I do is I give the dose value in a data frame. So I say data frame dose is equal to 40. So I say use a dose of 40. And I specify the interval type because we'll compare it with a second type that's commonly used. So interval is equal to confidence. So let's see what we get here. And we quickly get the results returned to us, and we're told that the interval around the 1902 is from 1705 to 2099. So from 1700 to 2100 effectively. So that's where we draw our error bars around the value of x. Now, of course, we could do that not just for 40. We could do it for 41, 39, 42, 38. In fact, we could do it for every value of dose. Let's just choose integer values from 10 to 80. So we can actually get the software to do all these for us. So I set up here in line 19 a vector of x values, which are basically a vector from 10 to 80, because these are the values of dosage that we're seeing here in terms of the whole numbers at least. And then what I can do is use this predict function not just to get a confidence interval for one value of x like we did for 40, but to get it for all 80 or well 70 values, isn't it? And so if we look at, and I stored an object called preds, and if we call up preds, we get a big data frame actually back. And what we have is in the first column of this data frame, we have the actual fitted values, which correspond to the points, of course, on this red line. So if I tried to, so for example, plot this like a curve sketch, I would simply be recovering this red line. But we also get these lower confidence limits, that's what the LWR means, for each value. So the first one is for 10, the second one's for 11, the third one's for 12, and so on. So we could plot the error bars for every single integer value of dose across the range. And of course we have the corresponding upper value of the error bars. What I could do is take these and plot a point for the upper confidence limit for 10, 11, 12, and so on, and actually plot it just like a curve sketch. So use basically the same curve sketching approach we've used before, using these upper confidence limits. You know, the first one is plotted against 10, the second one against 11, the third one against 12, and so on, all the way up to 80. And I could repeat that for the lower confidence limits, and what I'd be represented then would be like a curve sketch of the 95% confidence interval around the fitted curve here. So I think I'll go on and do that. So I've done the curve. So in the next one, and I've done the plot, so I don't need to do it again. In the next one, I get lines. So this adds a line to a plot. And I'll just explain the syntax here. I'm plotting the x values we used, I set up a data frame with x values, and they had all the dosages, 10, 11, 12, for example. Let's just look at it here. So x values, dose, 10, 11, 12, 13, 14, 15, and so on. So I'm plotting those values against their corresponding lower limits in the first case. So the way I extract the right column from the preds data frame is I put in preds, a comma, and I give the name of the column I want to actually plot, which is the lower column, LWR, or I could have just put in, instead of the quoted string LWR, I could have put in, it would have been 2, column 2, just put in the column number. And this is going to be red, and I'm plotting it as a dashed line. So line width is 2, just makes it reasonably thick so we can see it, and line type equals 2 makes it a sort of dashed line. Let's have a look at this. So that's what I've done there. Yeah, so these are the point-wise lower confidence limits for the predicted values centered on the solid red line. And then I can do the same thing for the upper confidence limits, of course, and I get a nice sort of visual representation of the 95% confidence interval. So there it is there. And you can see that it's not uniform. It's not uniformly wide. Sort of in the middle here it's wider, and over here it's a bit more narrow. It seems to get wide again. So there's a sort of complicated relationship between where you are, what X you're using, and how wide your confidence interval will be. But this is what represents what we call the point-wise confidence intervals for each predicted value using inputs, or for a predicted value, for a predictor 10, 11, 12, 13, 14, 15, to see roughly how precise we are being in estimating these values. Can we just clarify before we go on to the next part what this is. So, okay, this is the confidence interval. Okay. This is for the population mean response. In other words, what that interval is capturing is a interval or range of values within which we are 95% confident that we are capturing the true population average response given that value of the predictor. So it's the population average estimate that we're actually getting here in terms of this interval estimation technique. Now that's often of some use. You want to know what the population average will be given a certain input. But what if you're interested in a range of values where you capture not the population average, but 95% of the entire possible responses from a population? And the dose response data might be a perfect example of that. So what we have here in terms of our picture is an interval and saying, well, the population average response to a dose of 40 is somewhere between the upper and lower confidence limits. But what if we say, well, that's not good enough? What we want to know is it's not good enough, because if people have very extreme, or in this case, mammals have very extreme reactions to this steroid, it may be, for example, medically dangerous. So it's not good enough that the average response will be within a safe range. We want to know whether individual responses will be within a safe range. And this interval isn't capturing that. This is an interval that indicates how precise you are being in estimating the population mean response, but not the individual responses. So we'll contrast this with the next thing, which is, I'll use blue for this, what we call prediction intervals. Now be a little bit careful with authors. That you're reading, because although many use the terminology I'm using here, it's pretty standard to differentiate between confidence intervals being for a population mean response and prediction intervals of being for a range within which you'll find individual new responses. Sometimes people aren't that strict with their terminology, so just make sure that the author you're looking at or the website defines what they mean by these things. So prediction intervals. This is an interval that captures a percentage typically 95%, but it can vary, of individual responses given the predictors. Okay, so what we're saying is, for example, if we give a dose of 40, give me a range of values where I would expect to find, let's say, 95% of all responses from individuals. Not their mean response, but all responses from all individuals. And that's called a prediction interval. So it's at the individual level. The formula for this actually is very similar, it turns out, when you work through the mathematics. It's y hat I plus or minus the t value, with the awkward notation, and now it's the square root of s squared plus the variance of y hat I. So it's the variance of y hat I again, that complicated thing, plus you add in another s squared value. And this is what it turns out to be. So it's very similar, but the reason I write out the formula is, in particular, you'll notice that if I add on the s squared value in here, that means that this interval is going to be wider. It's going to be somewhat wider, and how much more wider it is compared to the confidence interval will depend on the value of s squared. If this is big, then it's going to be quite a bit wider. If it's small, then it's going to be quite close, but a little bit, in other words, only a little bit wider than the confidence interval. Let's go and plot that on OR and see that in action. So what I can do is I will do another plot here. So there's my confidence intervals. And now down here what I'm doing is I'm setting up a thing called PREDS2. So I'm going through exactly the same procedure. So I'm repeating myself here. But instead of using interval confidence, I'm requesting from the predict function the interval of type prediction. And that will add in that extra s squared term. And I'm going to use the same plotting then when I get this out, but I'm going to use dark green for the prediction intervals, excuse me. So let's go through this. And I'll have a zoom here. And this is what we get. So we have the solid red line here that is a function that represents the fitted values. We have the red dashed line that represents the confidence interval for the mean response given a value of x. And we can see it's quite a bit further out is the green line, which represents a 95% prediction interval. In other words, an interval within which we'll expect to find 95% of all individual responses given a value of x, the dose of the drug in this case. And in things like drug development, that might be very important. There's no point in having a mean response to a drug if 20% of people have a dangerous reaction, either high or low, to that drug. So you want to maybe estimate where you expect to find most responses. And so be careful when you're reading websites and so on about prediction and confidence intervals. Make sure the author defines what they mean by those terms. Sometimes they're used loosely, but for example, software like OR uses them quite precisely, as you've seen, in terms of keywords. Okay, so that's some discussion of the ANOVA table of estimation, of predicting or estimating using a multiple regression model, and we'll see use for that as we go through the module. Thanks.